going. Here's your 700 low right off of or near Atlantic City. 50 knot southeasterly winds just ramming right into this gradient. And the winds just to the north of your temperature gradient are from the north at like 20. So you're having all sorts of confluence here, speed convergence. You actually have a 700 warm front starting to form. So you're having all sorts of focus in this area. So at this point, your deformation should be pretty extreme, and it really was. It really tightened up and covered a lot more real estate. And you can see that the GFS forecast was a 12-hour forecast at 12Z Sunday morning, 7 a.m. It's focused right from Hartford, Connecticut down into the New York City area. So you look at the frontogenesis, since your deformation was acting on that temperature gradient, your frontogenesis really continues to strengthen. It continues to tighten. The gradient tightens, frontogenesis straight just gets really intense. So at 7 a.m., obviously, you really have your band going. Send it down from Hartford. At this point, I think we're getting like 3 to 4 inch snowfall rates. So now, basically at 1 p.m., your upper lows east of Long Island. Your temperature gradient on the west side of the upper low is not as extreme. It's pretty tight, but the winds, the convergence isn't that great anymore. In fact, the whole area of real frontogenesis looks like it's moving up into the Gulf of Maine. And when you look at the deformation, it's definitely lifted up into the Gulf of Maine. You look at your frontogenesis, it's all lifted up. So the band at this point really should be weakening and pulling east. And basically that's what it's doing. These mesoscale bands don't last for a long, long time because of that circulation that we showed that develops. It actually eventually puts the atmosphere back in the thermal wind balance, so your band's actually going to kind of disband, really. So I just kind of have a brief loop here on the radar loop with the frontogenesis overlaid. It's kind of hard to see, but what we want to focus on are these contours here, these positive contours that eventually move up into Maine. The negative ones are not frontogenesis, but frontolysis, where your front's actually falling apart. So you can see how, well, I'll wait until we, actually what I'll do is I'll just go to the next slide, because it's the same thing, it's just still. Pretty strong frontogenesis. Basically on the, this is the NAM 40, so the 40-kilometer scale. Anything over 100 units is pretty good. But the thing is, it's pretty broad. It's a really broad area of frontogenesis, so you really want to tighten it up in order to get a nice, narrow, intense band. So basically, that's what happens. Look how your axis of frontogenesis really starts to tighten up, and the band does the same thing. So that's at 9Z. So this one, it was really going crazy, New York City area. Really tight. It can't be more than, what, 30, 40 kilometers, if that. And as soon as that tightens up, notice that the heaviest snow, the yellow here, is just to the east of the frontogenesis. Say the frontogenesis axis is right down the middle here. Your heaviest snow is almost always going to be on the east side of that because of that vertical circulation. Say the circulation is centered in the middle of your frontogenesis. On the warm side, which is the east side in this case, that's where your upward motion is going to be. Therefore, your heaviest snow band should be just on the eastern edge of your frontogenesis axis. Yeah.
Any vorticity maxes on there that concentrate the lifting mechanism that you might see? This is 600 millibars, but on a 500 millibar chart, would you, for instance, would you be able to see some little vorticity maxes?
Well, you would. I mean, there's a big upper low at 500 that's developing just to the east here. Vorticity does play a part, especially in band, not in band strength necessarily, but band orientation. Notice how the band pivots, and that's how New York City got crushed, because
a lot of times the frontogenesis is tilted too. That's
right, and I'm going to show that in the cross section. It's pretty cool. So here's 9Z Sunday morning, the NAM 12 analysis. The green here is frontogenesis, so these values over 200 are pretty extreme. And the image here, the blue and purple that you see, is actually instability. So basically what you have is you have the frontogenesis, and the frontogenesis is so strong that it's actually creating instability, or we call it CSI if it's slantwise. A lot of people have said that you look at cross-sections and you say, well, let's look for our frontogenesis and maybe some CSI or instability will vect into there and help the updraft strain. It's actually not the way it happens. The way it happens is the frontogenesis becomes so strong, it takes your theta E surfaces and tilts them, and basically that causes your CSI. So I'll show this actually in the cross-section here. So basically, here's a cross-section taken from the southeast portion of the cross-section is taken from well out in the ocean southeast of Long Island. And the cross-section extends northwestward across Long Island Sound and to the south of Albany. So here's southeast of Block Island, and here's near Poughkeepsie somewhere. And here's 850, 700, and 500. We were just looking at frontogenesis at, say, 700 or 600 millibars. That's not really the way the air mass is. You just don't find things on a level plane. Everything in the atmosphere happens in the vertical. When we look at a 700 millibar map, we're only taking a slice through this area of frontogenesis here, and that's what we're looking at in 2 dimensions. But here, your frontogenesis, what really happens in the real world is it slopes upward. To the south of your warm front, or the surface warm front, is going to be here southeast of Long Island, and your frontal boundary exists all the way up through 850 to 700 and slopes back into the cold air. And basically what happens at that point, you have your frontogenesis maximum here in the mid-levels. And like I said, you get that circulation going. You're going to have vertical motion on this side. In fact, you can see it here, 20 microbars per second on the warm side of the frontogenesis band. And downward motion, which is the negative dashed area here, on the cold side. So you have your circulation going, downward motion here, upward motion here. And that's at least this AWIPS program actually stops at 20 microbars. There's probably like 40 or 50 in the center here. So you have a vertical, a tight and very vertical orientation of your omega. So this is where your band's going to form and fall in here. And when you start getting these vertical motion values that strong in there, you can snow at 3 or 4 inches an hour. And when that really starts to crank, you end up with instability. We call it CSI. And what happens if you have upward motion here, your frontogenesis band, your air is going up very fast, and then it encounters a region of instability. It's going to go up even faster because the atmosphere is unstable. So you're going to actually enhance your snowbanding because the instability actually constricts your band, and when it does that, it gets heavier. So 10 miles away, you might not be snowing that hard, but 10 miles, like say, in New York City that morning, snowing at 4 inches an hour.
Mike?
Yeah.
Did you find, what did you find as the primary, was it CSI or CI?
I was going to put that here, but I thought that was going to be a little complicated. Okay. But what you actually have to do is you actually have to overlay your theta E sub-S surfaces and your momentum surfaces. Right. And for a time, there was actually both.
Okay. Because I know CI, usually vertical convection is favored over slantwise convection.
If you're just unstable in the vertical, just like regular instability, it's always going to dominate your slantwise instability. Right. But there are times, and I think in this case, I could probably bring it up. I may have a few extra slides.
Jim Moore, before he died, did a paper with somebody, and they had a conceptual